it's about time to move on to our next topic, which is going to be adopting a robotic testing platform in wastewater treatment facilities. We've got Bochin Zhang and Iris. I see you're online.
No, it's me again.
Oh, no, it's Martin. Okay,
Yeah.
sorry about that.
No worries.
So Bochin is a PhD student at Stanford, monitoring and sustainable design and construction under Civil and Environmental Engineering Department. His research interests are applying operations science principles and process simulation methods for supply chain management of prefabrication modular construction. Bochin has industry experience working in major general contractor firms as a construction analyst. So we'll turn it over to the two of you.
Yeah, so I'll kick it off with just a few comments, and then Bochin will run through the bulk of the presentation. Also, want to acknowledge our collaborator in industry, Amanda Piao, who leads this the company that provided case study over in China. So I would say since the last, and thanks for having us here in the in this symposium or conference. Since the last conference, one thing that I have come to realize, and I realize that's not going to be news to Todd, James, Gary, Roberto, and probably many others, is really the versatility of project production management methods. I mean, broadly speaking, what we've seen is these methods are very, very helpful in identifying bottlenecks. Of course, production bottlenecks to control production. So that we are in charge and not subjected to chaos. That's going to be Sarah's talk from our research group later, developing methods to actually get data very quickly and consistently and automatically so that you can actually understand the production system and then understand the bottleneck and control it. But also, just in the talk just now, right, we can see undesirable production modeling helping us identify undesirable bottlenecks that point to misaligned information or resource flows when different production systems come together have to come together as an integrated demand supply system. And thanks, Todd, for the comments there. And I think this is something we can work on together as a community to really create individual and system level optimal performance. But another one we have seen is, and that is the talk here, is in terms of bringing innovations into our workflows, such as AI methods or robotics, to mention a couple key ones. And obviously here you can see from the title this is focused on robotics. It's always difficult to know, at least in my experience, how much investment should you make, and at what level, what scale, with what focus exactly, and how quickly, to improve a production system. And so I've seen numerous misalignments in terms of expectations from innovation and overinvestment, underinvestment. And as a result, the result is always, less, the production system isn't improved as much as was promised or hoped for. And so here in this talk, you will see how we're able to use production system modeling to understand the impact of novel methods that then guide you in terms of how to best scale these innovations. So with that, I want to turn it over to Bochin.
Thank you, Martin. Thanks for the remark. So last year, in the second PPI technical conference, Martin and I shared how operation science principles and production system optimization can be used to optimize the offsite construction supply chain. And this year, we would like to further extend this method to the critical infrastructure sector, specifically on evaluating the operations impact of implementing automation in a wastewater treatment plant in China. Oops. Okay. Let's begin by why we're looking at a wastewater treatment plants in China. As you may know, China operates the world's largest municipal wastewater treatment sector, and this sector currently is under immense operations strain. The rapid urbanization and industrial growth in China actually overwhelming these older plants many of which were built between the 1990s and 2010s, without advanced automation or sensing technology helping with the operations. And as a result, most plants rely on labor-intensive operating processes. And because of the demand, the average operating load of these plants is reaching above 85% of the design capacity by year of 2019. So you could imagine it's still increasing throughout these days. And this creates significant challenges in operating these wastewater treatment plants in China to meet the environmental regulation on discharges and also at the same time operate within their budget targets. And this is where we see a clear opportunity for implementing automation and also thinking from the operations-based perspective to improve the situation. So working with Sequoia Libre technology, we explored whether the robotic wastewater testing platform could create measurable operational benefits in one of the wastewater treatment plant in North China. The case study showed up to 71% cycle time reduction across a major pollutant test. It's a total saving of 198 minutes for each of the tests in one day. There's a significant reduction in sample queue time for 144 minutes, out of that around 200 minutes. There's a 50% reduction in the daily testing duration from 6.6 hours to 3.3 hours. So the plant actually can run more tests. And analyst work hours utilization reduced from 32% to 8%. And the role of the analyst shift from operating the test to actually supervising the test. Beyond efficiency, the robotic system also enabled real-time monitoring with 1 to 3 hour forecasting capability of the effluent quality. This actually creates a digital feedback loop that the manual system simply cannot match. And these results show the significant positive impact on improving the operation of this wastewater treatment plant and help the leadership team of the plant to make an informed decision on adopting this automation in their process. So let's take a look at the case study. We studied the Xinyi wastewater treatment plant in Harbin, China, which is really north part of China, close to Russia. The plant is commissioned in 2011, located near Songhua River, which is one of the biggest in the local community, serves around 85,000 residents. It utilizes a AAO treatment process with 100,000 cubic meter per day design capacity to treat wastewater. The goal from the management team of the plant was to improve the testing throughput and increase the testing frequency of the effluent pollutant level to ensure the effectiveness of the treatment under high operation load. So we first studied what is the AAO wastewater treatment process, and this is a simplified schematic. The process, why it's called AAO, is because the process involves treatment reactions in the anaerobic tank, in an anoxic tank, and oxic tank. And it basically removes pollutants, including chemical oxygen, demand, ammonia, nitrogen, and phosphorus. To provide adequate treatment, it is important to monitor the pollutant level at both the influent and effluent of the process in order to know how much the treatment is needed and the effectiveness of the treatment after the plant discharge the wastewater to the environment. In a current setup, a lab analyst collects samples manually at the inlet and outlet of the plant and conduct the testing once per day. Since the testing duration is pretty long, it's almost 8 hours. You can only come back the other day to conduct another test. The process is also from the interview of the plant team, the process is prone to uncertainties due to human errors, staffing shortages, and inconsistent testing quality. So with this downside of the manual testing process, the plant management team is leaning towards automations. But before they really make the decision, the management team would like to know how can they rigorously assess the operational impact of adopting a robotic automation in this wastewater treatment plant setting. We interpret this question into specific questions like what are the impacts on testing cycle time, process variability, and analyst utilization? How can this robotic testing platform support predictive monitoring and proactive treatment so they can adjust their treatment process accordingly? And last but not least, is the investment justifiable from a process performance standpoint? As I'm quoting from the plant manager, we needed a way to rigorously assess whether the automation can address our issues in a measurable and justifiable way. So we begin by mapping the baseline, the manual process. There are 4 major pollutant tests conducted simultaneously every day, including from the top to bottom, ammonia, chemical oxygen demand, total phosphorus, and total nitrogen. All tests are done by a single analyst working on an 8-hour shift. It's basically have to jump around these steps in order to keep all the processes running almost at the same time. Using analytical modeling function in the software developed by SPS to analyze the baseline process, we find the total average cycle time of all these tests was around 400 minutes. The analyst utilization was 32% under his 8 hours work time because he actually has times waiting for the reactions, and in that time he is actually focusing on other jobs, and then he's coming back and moving forward, always back and forth. And we utilized the scored coefficient of variance of 1.0, which is high variability for manual process in analyzing. We also then simulated this manual process using the discrete event simulation function. For the scenario, we are showing one of the scenarios. We actually run 50 scenarios. The scenario shows actually incurs a 6.8 hours duration for the overall 4 testing in a day. The average of the 50 tests was 6.6 hours. What this figure is revealing is that the process duration is not only justified by the average processing speed, all the blue bars, but also by the time range of each of the process steps. So basically, in this case, we see there are chances that this process will be affected, and then the total time could go over the 8 hours, and this will incur over time for the analysts. And we were able to validate this with the plant team, and we use this as a benchmark for comparison. So next, we investigated the robotic system provided by the Sequoia Libra technology, which automates sample collection at the inlet and outlet of the plant. But also, the system was integrated with IoT devices that provide additional sensors monitoring the in-process indicators, such as nitrate and ammonium in the reaction tanks, to inform the management team of the effectiveness of each of these treatment steps. This process is supervised by just one technician, shifting from the role of operating the test to actually just supervising the test. When we then map this robotic testing process, the robotic testing platform fully automated process steps, including sample preparation, test operations, and test reports. The analytical modeling again showed dramatic improvements in the cycle time reduction from 400 minutes to 200 minutes. Analyst utilization reduced to 80% as majority supervising jobs. Basically, also we use a 0.1 for low variability in this automated process. The schedule simulation results align well with the analytical findings. The average daily test time decreased to 3.3 hours, nearly a 50% improvement. And from the schedule, from this figure, we can also see that automation was not just increasing the time for processing, which is the blue bars actually reduced, but also it makes the whole system be more stable. The duration range of each step is narrower compared to the previous schedule. So here's a detailed comparison across the 4 pollutant types. You will notice the dramatic time savings ammonia testing dropped 70% because it's a lot of time this process was involved with moving samples around different testings. The chemical oxygen demand, total nitrogen, and total phosphorus, these tests are each seeing around 38% to 55% reduction in their cycle time. The analyst utilization again reduced, and the daily testing duration was reduced 50% to 3.3 hours, which means at least they can do another test in the day. So they get them more data to understand the process, the treatment process. And we see this as a clear example of how automation shifts the process performance frontier. But one of the interesting insights we see from this analysis was the robotic system wasn't just increasing the speed of the processing, but it's also reduced the process variability. For example, in a figure at ammonia sample flow, the raw process time for it is around 0.5 hours and was reduced to 0.3 in the automated scenario, but the queue time was actually reduced to almost zero from 0.5 hours. From interviews with the plant team, we want to understand that in the manual processes, the process cycle time could be affected by inconsistent sample handling, differences in analyst skills and timing, equipment calibration fluctuations, and irregular workflows due to shift changes or urgent reprioritizations. These are all factors that could actually hinder the testing samples to flow in the process and leading to this large range in the testing cycle times. Or on the other side, a robotic testing platform actually improves this by standardizing the procedures, automating the sampling and testing operations. And this significantly reduces the process variability, and therefore we see there's a reduction in the queuing time and ensuring the whole process will produce consistent, reliable, and timely testing results. And this is very critical for the team to operate the plant. But beyond improving all these testing efficiencies, we're also looking at a bigger system. So the robotic testing platform also enables a proactive control of the ALO treatment process through these data and predictive monitoring. So this is an example, and this is the dashboard showing the real-time data was collected by the IoT devices on the line, on the treatment line, forecasting for the chemical oxygen demand concentration at the effluent of the plant for 1 or 3 hours. The plant management team then used this forecasted result to proactively adjust the treatment steps, such as reactor temperature, because it was really cold in the north area, and the chemical dosing to save energy consumption and operational costs. It also supports daily report generation, further reduce administrative overhead for the analysts. And we believe this moves the whole plant closer to a digitally managed operations systems. So in summary, the operation science principles and production system optimization still help us to provide a method for us to evaluate automation's operational impact in the context of wastewater treatment testing process. The robotics testing reduces testing duration, variability, and analyst workload. A high-quality, real-time pollutant concentration data supports a predictive process control, which augmented the capability of the analyst and the management team. And most importantly, this evaluation allowed the plant leadership to make an informed investment decision backed up by operational evidence. And at the end, the Xinyi Wastewater Treatment Plant's management team moved forward with this robotic testing platform with a clear goal to enhance their testing process stability, reduce the cycle time, and improve the responsiveness to pollutant fluctuations. That said, this work still has some limitations. The squared coefficient variance estimates we use 1.0 for manual with limited empirical data. We didn't really model the rework and failure scenarios, which will be largely affect the whole process in a day. And also the future work needs to consider the regulatory recognition of using the robotic platform under the supervision of the analysts. The current law is actually requiring the factory to have to test the major pollutants manually throughout the day. But as the quote from our point of contact in the Sequoia Labor Technology, the project manager basically that he said the lessons from this case study on redesigning and automating the whole wastewater testing workflows with digital technologies are transferable to other infrastructure systems and offering an approach to enable data-driven operational transformation in support of China's digital infrastructure initiatives by 2035. With that said, actually, Shane, this whole team obtained funding from the government to really implement this robotic platforms, and the government is actually using them as an example to think about how they can actually improve the law and the regulatory to allow for more automation and digitization in operating these critical infrastructures. So with that, thank you very much for listening, and we're happy to take any questions.
Very good. Again, if you got any questions, drop them in the chat, drop them in the Q&A. Maybe I'll get the ball rolling here with a quick question. When you started the work to model it, the production system, did you look at other alternatives other than automation to improve performance?
So with the specific request from the plan was to evaluate
Automation.
the automation process and then compare that to the baseline of their manual process. They are, of course, they are looking at alternatives, but that's out of our scope.
Okay, I'm just curious.
Yeah.
What you've clearly demonstrated is the power of using production modeling on a system to enable decision making and get more done with less. That's
Yes.
exciting stuff. Very pleased. And I hope our audience is connecting the dots here. It doesn't matter what you evaluated here, really.
Mhm.
What you evaluated was a production system and the methods you went about to evaluate that production system and to optimize it, provided meaningful information for decision makers to decide which direction they wanted to go. That can be applied to any production system, right?
Yeah. Yeah,
Now
exactly.
you're probably seeing production systems all over the place, huh?
Yeah, exactly. So I think we are considering an administration process could be also a type of the production system because we are actually facilitating the flow of the testing samples in the system.
Mhm.
And but what we are connecting the dots for the management team of that factory or of that plant was that they of course observed the downside for the manual systems of all the human errors and all that, but they were not able to connect these downsides with the performance of the system to say that this is actually affecting by how much their overall time and resources used for and efficiency of operating the plant. And also overall, this method was able to demonstrate both quantitatively and qualitatively on this. And that's actually shift the mind of the whole management team to think about, oh, this is something we can never do, even though we could have another 100 analysts be put in the system, but we're not going to be improving for example, the variability, the stability of the process because it's still going to be human beings doing it and then we'll see the variabilities. But what they also see is the value in human beings to do analyst jobs, to do supervisory jobs. It's not to say that we're going to fire the analyst to and then just purely shift to the automation. It's like the data and then the new process is actually augmenting the capability of these analysts. And they could see that they could operate the plant with the same number of the people, but they have a more capabilities to run it more efficiently.
Mhm.
Yeah, I would say just to build on that a little bit, Bochen has really, I think, for me, created a great example of this kind of digital twin of our production processes that I know you have talked about, mentioned quite a lot. And what I really mean by that is we need those digital twins to be visual so people can talk with each other. The different people in the different roles and functions can be on the same page. That's very much like a 3D model or a BIM or whatever you want to call it, or a 4D model for the things we build. And then here is how we actually get something done. And so we, of course, need those visual models, but that's not enough because we've had those for a long time. But having them directly connected, like a building information model would do in the building sector, for example, with the data, with the analytics, creates also, the blueprint, not only for, who needs to change what to get better performance out of the system, but also how does the system actually need to operate. It creates really the system specification. And then it creates the feedback loop, as I was mentioned before in previous talks, needed to continuously improve them.
That's really good. So what's next for you, Motion?
We are also looking for more production processes. We're looking for opportunities to collaborate with different types, different industries, to help them to improve their processes. We do have opportunities to look at, for example, the data center processes. And then, we'll start from there.
Good. So if anybody has an interest in following up, they just reach out to you and see where it goes. All right. Excellent. Well, thank you very much for taking the time and effort to write the paper and present your findings.